Hello, greetings to you all once again, and you are welcome to another exciting video on Applied Electronics tutorials. So we are done with the calculus, right? And I'm trying as much as possible to cover all the sessions under Applied Electronics before you write your final exams. Are you okay? So today our video will focus on the operational amplifiers, which is popularly known as the op amp. So if someone say op amp, what is actually an op amp, right? So it is an electronic component that increases the voltage. It increases the voltage of a signal, right? So that's the main purpose of the op amp. So the increases can also be written as amplifies, right? So it amplifies the voltage of a signal, right? So that is the main function of an operational amplifier. So all that it does is it increases the voltage. Okay. So let's typically draw a sample over here. Sample of an op amp. Like we have something like this, right? And we have minus here and plus at this end. You get it? Any of them can be minus and any of them can be plus. So let me consider this side as minus and this side as as plus. Okay, so normally this is the output of the device, right? So here the output, and this side is considered as the inverting input. So we have two types of input. We have the inverting input, and we also have the non-inverting input. That is the positive side is considered as non-inverting input. So you should take note of it. Inverting input. So we have the inverting input, which is the minus, and non-inverting input as the plus. Okay, so let's look at the image over here, right? So op amp can be ideal in an ideal situation, or it can be in a practical situation. So practical situation is more like when we have the components and we've mounted it on a circuit board and it's working physically, right? An ideal situation comes with with the software. So assuming I'm simulating it, I'm going to get ideal situation. But when I'm building it physically, right, then it goes with a practical situation. What actually comes about when, let's say, I'm building it physically. Okay, so we are going to differentiate between the ideal situation and the practical situation. So this is the ideal situation, ideal, and we have the practical situation, right? So what's the results? So for the ideal situation, right, what do we have? With the ideal situation, we can say that, right, the input impedance is infinite. So we have infinite input impedance, right? Infinite input impedance. That's for the ideal situation. But what about the practical situation? We have an impedance, but it's very high. Okay, so it has a very high input impedance. So very high input impedance. Right. Yes. Then again, we can see that the voltage gain for the for the ideal op amp is infinite as well. So it has an infinite voltage gain. But with this one, the voltage gain is very high. It's not infinite, but it's very high. So with the ideal, it has an infinite voltage gain, right? But with the practical situation, it has a very high a very high voltage gain. Do you get it? Yes. Then what again? We can see, right, that the output is 0. The output impedance is also considered as 0 over here. Okay. But here they recognize the output impedance. We have an output impedance at this end. So how can we differentiate it? We say that output impedance is 0. So it has 0 output impedance. 0 output impedance. Right. Then we also have what? We have a very low output impedance. Very low output impedance. Do you get it? Then what again? We can also consider the bandwidth, which is not showed here, right? When we say bandwidth is more like the difference between two frequencies. Okay, so it deals with frequencies. So practically, let me just give a typical example. I have a frequency f1 here and a frequency f2 here. So if I want the bandwidth, then I just need to find the difference, right, between these two frequencies. That's actually what is called the bandwidth. Okay, so with ideal op amp, it has infinite bandwidth. It means that the bandwidth is very, very large. It goes to infinity, right? So it has an infinite bandwidth, right? But with the practical, right, it has a very high bandwidth. So with this, it's very easy to learn, right? All the infinites becomes very high for the practicals, and all the zero becomes very low. So it's very clear and it's easy to learn, right? The next thing that I want to talk about the op amp is what is termed as the common mode rejection ratio, right? It's also very, very important. That is the common mode rejection ratio, which is popularly known as CMRR. CMRR, right? That is the common mode rejection ratio. What is it about? If someone should ask you what is common mode rejection ratio, you will say that it is a measure, right, of its, that is the op amp, its ability to reject input signal that are common to both inverting and non-inverting inputs. Both inverting and non-inverting inputs. So we have inverting and non-inverting inputs, and this one might have a similar in the signals. The signals might be the same. Like, so the CMRR, right, is the measure, right? So we are measuring the op amp's ability. Let me change this one to see op amp, right? Ability to reject, its ability to reject input signal that are common, right? They are common to both the inverting and the non-inverting input. So common mode rejection ratio, right? And what is the formula for it? CMRR is giving us the open loop voltage gain, all divided by the common mode voltage gain, that is CM, where the OL stand for open loop and the CM stand for what? Stand for common mode. Right, we have the common mode, and the A is a gain. A is the gain. So we have the open loop gain and we have what? Common mode gain. So this is a typical formula or the general formula for what? Common mode rejection ratio. So any question that they give under common mode rejection ratio, they are going to give you these values and you just insert. Also in the question, right, you can be asked to convert it to what? To decibel. Okay, so converting it to decibel is just going to be what? CMRR equals to what? Equals to 20 log of what? Of the open loop gain divided by what? Common mode gain. That is, if I want to convert it to decibel, D capital B or decibel, the spelling is DECIBEL, right? So if I want to convert it to decibel, I just need to find 20 log of what? Of the final answer. Let's take a typical example, right? So example 1. The question says that a certain op amp has what? Has an open loop differential voltage gain of 1000 volts per watt per millivolts, right? And a common mode gain of 0.4, right? He said that we should determine what? The CMRR and express it in what? It in decibels. So with this kind of question, it's very simple and it's straightforward, right? We know that the, how do you call it? The AOL is equal to what? 1000 volts per watt per millivolts. In that case, it's the same as 1000 volts divided by what? 10 exponent minus 3 volts, right? And with this, if I simplify, I'm going to get 1000 times 10 exponent what? 3. That's if I should bring it to the denominator side, which is the same as, is it 1 million? Yes, 6 zeros. Okay, so I know the OL to be this, and I know ACM to be what? 0.4. So in that case, the CMRR is simply going to be what? AOL divided by what? Divided by, how do you call it? ACM. Do you get it? So what do we have here? We are going to get, how do you call it? 3 zeros. That is 1 million divided by what? 0.4, which is the same as 1 million times what? Times or divided by, let me make it clear to you, 4 on 10. Okay. So with this, what do we get? But you can use calculator straight away and you get the final answer. So we have 1 million times what? 10 divided by 4. 4 goes into itself 1. 4 goes into 3 of them. 25. Right. So at the end, what do we have? 25. How many zeros? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So that will be the value. That is 2,500,000. Yes. So in decibel, we are going to convert it to decibel. So what do we have? The CMRR is simply going to be 20 log of the final answer, which is 2500, 3 zeros again, right? And this one should end up giving us 128 decibel. You can use the calculator to compute. You're going to get 128 decibel. So that is how we compute for the common mode rejection ratio, right? So you should take note of it very well. Now there are certain terms in op-amp that you need to know, right? I'm going to talk about the certain terms in op-amp. The first one that I want to talk about is the input offset voltage, right? That is, sorry, my writings is changing. So I want to talk about the input offset voltage, right? Now what is it about? We say that the input offset voltage is the small voltage. Take note of it. The small voltage that must be be applied between, right? It must be applied between the inverting, right? Inverting and non-inverting inputs. Non-inverting inputs of an op-amp, right? Op-amp to make to make the output zero, the output voltage zero. This is one of the most important things, right? So you say that it is the smallest or the small voltage, you get it, which must be applied between the inputs, that is the inverting and the non-inverting inputs. Okay, that will make the output voltage zero. So you want V naught to be zero, right? So since we want V naught to be zero, that is if you draw the operational amplifier, right, minus plus, so inverting and non-inverting, and this here is where we get our V naught. We want it to be zero, right? So the small voltage that can be applied between the inverting and non-inverting input to make V naught zero is called the input offset voltage. Okay. The next thing that we want to talk about is the input bias current. Input bias, right? So the input bias current. Let me clean it well and write it again. So the input, right, bias current. And what is the input bias current about? Right. It is the average. So it is the average current. Average of the current. The current flowing into the inverting the inverting and non-inverting what terminals of an op-amp, right, which ideally should be zero, but is non-zero in practical op-amp. So it should be zero in the ideal op-amp, but it's not zero in the practical op-amp. So that is basically, for instance, if I have the op-amp here, right? So I have the inverting side, which is minus, and plus non-inverting side. So the current flowing here, let's call it as I1, right? I1, and the current flowing through this one can be called as I2, right? So with this, I will say that the sum of it, or the average between the current that is flowing through both inputs, that is I1 plus I2 divided by 2. So that is what is called the input bias current. So it is the average of the current flowing into what? Into the inverting and the non-inverting terminals of an op-amp. Right. So that is it. And the condition is that ideally, right, it should be zero. In an ideal op-amp, it should be zero. For ideal op-amp. For ideal op-amps, right, this input bias current should be what? Zero. Are you okay? But in practical, it is not. So you should take note of it. Ideal is zero, but in practical, it is not. Then the next thing that I will talk about is the input impedance. Right. So we are going to talk about the input impedance. We've already explained that one, and let's talk about it once again, or let's give definition for it. So input impedance is the what? Is the resistance. Is the resistance that an op-amp what presents to the input signal, right, to determine, right, determining how much the op-amp, right, how much the op-amp will load the source, right, the source connected to it. Yes, so that's it. Normally it is more like the resistance between, how do you call it, this, right? So this is the input impedance. Okay, so it's nothing difficult. The same applies to the output impedance, which is over here, right? And what is the definition of the output impedance? The output impedance is basically what the op-amp present to what, to the load connected to its output, right? That's the resistance of the op-amp connected to the load to its output. That's it. So let me just write the definition here so that it becomes clearer to you. So the output impedance, right? So the output impedance is what? Is the resistance that an op-amp do what? Presents presents to the load connected to what? To its output, right? Affecting how much the op amp's output voltage can what? Can change in response to what? Varying the load condition. Okay, so that is it for the output impedance. Now let's move to the main agenda, right? Where they can give you a circuit, then you what? You calculate. You have different types of op amp, and I'm going to draw them here, and I'll attach the formula to it. It is your responsibility to know the formula, memorize the formula, so that when you get to the exams hall and they've drawn an op amp, you can apply the formula there, then you'll be good to go. So the first type of op amp that I'm going to talk about is the inverting op amp. Right, inverting op amp. With the inverting op amp, the diagram looks like this. Looks something like this. Right, and I have minus here and plus. The plus can come down and the minus can go up. Any of them can hold, right? The minus can also come down and the plus can go up. Are you okay? So at this point, you see the voltage is the V in is located at the inverting side, that's the negative side, and the positive is connected to ground, right? So that makes the unique distance, the unique difference between the inverting and non-inverting. So we have a virtual ground here. This side is termed as virtual ground, that is VG, right? So the VG indicating virtual ground, right, where the feedback is normally connected. So the feedback of the system is normally connected to the hot, to the virtual ground, right? So we have the RF here and the IF, that is feedback current. Okay, so that is it, and this is the input resistance, Rn. Then we have the input current also flowing here, which is In. But normally they will ask you to find what? The V out or the V naught. Okay. For the gain is given as the V out on what? On V in. Okay. And with this is equal to negative. Okay. So the V out normally, because it's connected to the negative side, it is always negative. That the V out is always negative. If it's connected to the negative side, right, the V out can be considered as negative. Do you get it? So it's negative. The reference, the how do you call it? The feedback resistance. The RF is termed as the feedback resistance. Feedback resistance, right? So it's given by negative of what? Of the feedback resistance, or divided by what? By the input resistance. You should take note of it. Right, this formula work. If as you prove it this year, it's going to take about 30 minutes of the video. If I should prove all of them, and I don't want to prove them, I just want you to know the formulas, so you'll be able to identify the type of op amp. Then you identify the formula which is associated with it. So this is an inverting op amp. Why is it an inverting op amp? Because we have a voltage and the input resistance connected at what? The negative side of the op amp. Take note, they can interchange the sign. The negative can come here and the positive can go there. Do you get it? And once it changes, don't be confused. Okay, the next type of op amp I would like to talk about is the non-inverting op amp. Right. So the non inverting op amp. How does it look like? So with that one, right, let me draw my op amp very well. My board is not straightened, so I'm struggling to write well. So with that one, I have, how do you call it? The positive can be up, the positive can be down. Okay. So the V in, or the voltage, is connected to what? To the positive, that is the non-inverting side. Then we have the input resistance connecting what? The inverting side, and we have, how do you call it? The ground. Do you get it? So we have the input resistance here, and attached to it, that's the virtual ground, we have the feedback resistance, that's the RF, right? And they are all having its way to the outputs, which is V naught. So the current flowing here is termed as IF. Then we also have a current that is what is flowing into what? Into the voltage. Are you okay? So with this one, the formula is giving us A equals to what? The V naught on what? On the V in, right? And at this point, we can see that 1 plus what? 1 plus RF, all divided by what? The Rn. That's the general formula. So again, you just need to know what? How the non-inverting op amp is drawn. Then you identify its associated formula. You get it? Once you do that, you are good to go. Once you do that, you are good to go. Then the next one that I want to talk about is the differential op amp. Differential op amp. Right. And how does it look like? With that one, both the inverting and non-inverting, they are having a voltage source. So I have plus here and minus here. Any of them can be plus, any of them can be minus. So with this one, I have an input resistance here. Let me draw it all. So I have an input resistance here, and it's connected to a voltage which can be termed as V1, right? So R in over here, right? Then we have, how do you call it? A resistor which is termed as the RF. The same way, we also have another input resistance over here, right? That is R in over here, and we have a voltage which is V2. Do you get it? And that one too can also have a reference or a feedback resistance. Do you get it? And they are all connected to what? To the output. Which is what? V naught. Right. So with this, we can say that the V out is equal to what? Is equal to the feedback resistance divided by what? The input multiplied by the difference in the voltage, that is V2 minus V1. So that is the general formula associated with it. So please always take note of the formula. It's a formula week, and once you're able to identify the diagram with respect to the formula, you are good to go. Right. So the next one that I'll talk about is the summing op amp. Summing op amp. Summing op amp, right? So with a summing op amp, it's more like one side, which is ideally it can be the non-inverting side, right? Is having multiple what inputs, and the non-inverting side is normally connected to what? To ground, right? But with this inverting side, I have multiple what? Resistance. That is, let's say R1. Then I have another resistance, that is R2. And I have another one, which is what? R3, right? And we have the V1 here, we have V2 here, and we have V3 here. And with it, we have a common resistor, which is termed as what? RF. That is the feedback resistor. IoT. They are all connected towards the virtual ground, which can be located at this point. Then it finds its way towards to the output, which is V out. IoT. And when it happens like that, then it means that the RF is going to be what? To be negative. Anytime it's connected to the negative side, then it's going to be negative. But if it's connected to what? To the positive side, then it's going to be what? Positive. You should take note of it. So with this one, V out can be equal to what? Minus into bracket what? Into brackets the feedback resistance divided by what? R1 times V1, right? Plus RF divided by what? R2 times V2 plus RF divided by what? R3 times V3. So that is the general formula. Okay, yes, that's the general formula for it. Then the last two that I want to talk about is the differentiator and the integrator. Right, that one is more like we have capacitors also attached to it. So we have the differentiator op amp. Right, so with the differentiator op amp, it's more like we have the op amp here, right? We have the minus and the plus. You get it? Then we have the output resistance, which is V out. Okay, but for the input side, that is the non-inverting side, or let me call it the inverting side, sorry, we have a capacitor over here, right, which can be termed as C. You get it? And there's a common ground, that's a virtual ground, which help us to connect what? The reference. How do I keep on calling reference? But feedback resistance, right? So feedback resistance, and it's connected to what? The output over here, which is V out. Okay, and we have the non-inverting side connected to what? To ground. Do you get it? With something like this, the V out is negative. You should take note. Anytime it's connected to the negative side, then the V out will always be negative. So we can say that the V out is equal to what? Minus the feedback resistance multiplied by what? The capacitor. Then we differentiate the input voltage. That is, this side is connected to the input voltage, right? We differentiate the input voltage with respect to what? With respect to time. And this one is giving us the differentiator op amp, right? So the last thing I'll talk about is the integrator op amp. That is the integrator op amp. Op amp, right? So with the integrator op amp, we have, how do you call it? We have the resistor rather being the input, and we have the feedback to be a capacitor, that is C, right? The feedback is rather a capacitor. So that's the difference between the integrator and the differentiator. So the feedback is rather a capacitor and the input is a resistor. Are you okay? So we have the output over here. Since it's connected to the inverting side, the output is always negative. Are you okay? Then we have the V in here. Then the non-inverting side is connected to what? To ground. So the V out can be expressed as minus 1 on what? On J omega R in C multiplied by what? V in. So you should take note of it. It's very, very important. Right. These formulas are very important. And once you know them and their diagram associated with it, you can what? You can solve questions. Okay, so let's solve one example, then we end the video. Okay. So with this one, right, how does it look like? It looks like an inverting op-amp, right, where the input voltage and the resistor is connected towards the negative side. So this one looks like an inverting op-amp, right? So the general formula is given by what? A is equal to what? V out or V naught, right? This is the same as V out. The V naught is the same as V out, right? So V naught on what? On V in, where this side is the V in, right? And it's equal to what? Minus RF on what? On R in. So this side is the R in and this side is the RF. Okay, so here we can just take this side of the equation to compute our V out. If they ask you to compute for the gain, it's very simple. A is simply what? Minus RF on what? On R in. So the gain is given as minus 30k over 10k over 10k, right? And this one is simply going to be what? Minus 3. Okay, but with the V out, we can say that V naught is equal to what? Minus RF on R in multiplied by what? V in. That is, we apply cross multiplication to get our value here, right? So what will be V out? So V out is equal to, this gave us minus 3. That is, the RF on what? On the R in gives minus 3. Then the input is 5. So and I'm going to get minus 15 volts, right? So that's it for the op amp. It's very simple and it's formula based. So on this note, I'll encourage you to solve the questions. If you have any challenge, you just let me know, right? So page 660 to 669. There are a lot of questions for op amp, the book that I gave to you. If you open to page 660 to what? 669. There are a lot of questions and formulas under op amp, right? So solve the questions there. And you see, if it's multiple choice questions, the ideal op amp and the practical op amp, those differences can be asked a lot. So try as much as possible to solve the questions there, and I believe that you'll be good to go. So I wish you the best of luck. I'm left with 2 more videos, and I'm assuring you that within this week I'll be able to complete the videos. Then you'll be good to write your paper. Okay. But on this note, please try as much as possible to also learn ahead, so that you'll be ahead of me. So once you watch the video, it's more like a plus to you. Okay. I wish you the best of luck. All the best. Bye bye.